Welcome back to chapter 4. Today we were doing triple integrals. Um, let's get straight to it. So, we're gonna kind of build up this intuition right here. In 1D, we have this idea in calculus 1, we have this idea of the fact that the area under the curve is the integral from a to b of fx dx, where this is y equal to a function f of x. So we put in values of x, and then we have a value of y for each value of x that we get, which we call f of x. Also, there's this notion right here that if we just do the integral from a to b of dx, we will get the length of b minus a. We will get the length of this right here. This is just the integral of a to b of dx is the length of b minus a. So the length of this line is the integral from a to b of dx. Kind of useless, but it gets more useful when we move into 2D. We know that there's the notion of the volume under the surface, z equals f of xy. You put in values of x and y, and then you get out a value of z, and that creates a surface. So 2 dimensions. The surface is, well, I guess you could say 2-dimensional, and then the third dimension is the height. So that's f of xy. That's the volume under the surface. But if you just take the double integral of the region R, in this case, of dA, that is your area of that region. The area of what region? The area of this region right here. This region. Or actually, I've been using the highlight, so I'm going to use the highlight. The area of this region right here is the double integral of dA. And we've already established that in our previous lessons. So in 3D, this is really confusing. Yes, I've actually drawn this. So we have the volume under a surface in here, but now we actually have a shape. This is our shape, f of x, y, z. Let's say w is equal to f of x, y, z. And then we have one space, and we're projecting one space to the xyz space in the w direction, which sounds really weird and sounds really kind of like I'm crazy. It doesn't really sound right. So we're finding the hypervolume of the space created by f of xyz under the shape, which is the space f of x of the xyz space, right? Like, yeah, I put what because that's really confusing. I don't know what that means. There is a notion that we could still use, though, is the triple integral of this integral, the triple integral of the region E in this case. In this case, is a plane, so we can't really find the volume of that. But if it wasn't infinite, then the triple integral of this region E is the volume of the region E, right? So this will not be possible because our x's span from from negative infinity to infinity. Or our y's or our z's, whatever the last variable is going to span from negative infinity to infinity, so it's not possible. It's infinite. But if we do calculate it like this, then if it's a closed region, then it has a volume. So what does this mean then? Well, we have to actually fall back into something in physics, specifically the fact that density is measured in like grams per liter, or kilograms per liter, and liters is actually a unit of volume, and kilograms is a unit of mass. So density, we use rho. In fact, I'll probably draw it a little bit better. It's supposed to have like this kind of it's not really a pea. It looks kind of like a sperm. That's why I set my videos to not made for kids, because it looks kind of like a sperm. So rho, that's what it's called. The Greek letter is called rho. Rho density is equal to mass divided by volume. So every change in mass is equal to rho times a small change in volume, right? So if we have mass is equal to density times volume, then a small change in mass is equal to density times a small change in volume. So if you want to find all of the masses, you add up all of the densities times small change in volumes, and you will get the mass of the entire object, right? So let's do this. Let's find the mass of the cube E, where this is the region for E, given the density function fxyz equal to this. So we just plug in chug basically. M is equal to the triple integral of E x squared y minus xyz dv, which is equal to what? Which is equal to the integral from -1 to 1 of the integral from -1 to 1 of the integral from -1 to 1. Now, does the order matter in this case? Not really, because it's all rectangular. I can kind of shift the bounds however I want. It's called Fubini's theorem. So that's what I'm going to do. I'm just going to do, x squared y minus xyz. I want to do the z first, because there's only one thing to integrate there. It looks simple. And then dx, or dy dx. So z dy dx. And why am I not moving the bounds with the variables that I'm integrating? It's because they're all the same variable. That's why. -1 to 1, -1 to 1, -1 to 1. They're all -1 to 1. dy dz. There you go. Or no, dx dz dy dx. I'm sorry. So what will this give you? This will give you, that's equal to the integral from -1 to 1 of the integral from -1 to 1 of x squared y minus xy is z squared over 2. Z squared over 2. This is going to take a lot of space. So make sure you have a lot of space for this. Double integrals already took a lot of space. This is going to take even more, so be ready. Dy dx. So if we evaluate this, if we put 1/2 in there, we'll have x squared y minus 1/2 xy, right? Yeah, alright. I was just trolling for a second. So this is equal to, I'm just going to evaluate this. This is x squared y minus xy times, or 1/2 xy minus x squared y minus 1/2 xy. And that looks a little bit sus, because what happens is this actually evaluates to 0, and that does not look right. Even though I made the question, yes, that does not look very right. But we'll see as we integrate. If we integrate it in another way, it should evaluate to the same thing. So this is equal to 0. So that means we're evaluating the integral from -1 to 1 of the integral from -1 to 1 of 0 dy dx. So that's 0. Now if we change the bounds to integral -1 to 1, integral -1 to 1 of, let's say, no, we'll do dy first this time, then dx, then dz. So x squared y minus xy, or let me put another integral -1 to 1 z. So we're gonna evaluate this another way now, because this is a little bit strange. So this is equal to x squared y squared over 2 minus x y squared over 2 times z from -1 to 1. Yes, and then -1 to 1, -1 to 1, dx dz. So this is equal to negative 1, 2, or no, evaluating this, you will get x squared over 2 minus xz over 2 minus x squared over 2 minus xz over 2. So yes, this is, I have more confidence in saying that this cube has mass 0 now. So this cube is weightless. It does not have any mass. There you go. QED. It does not have any mass. I made this question, did not think that it was not going to have any mass, but here we are. So let's keep going. How do we evaluate a triple integral using the kind of slices idea, the idea of x simple, y simple, and c simple, x simple, y simple, and z simple that we learned from double integrals. Now, obviously, it's going to be a lot harder to draw stuff in 3D. So we're going to try to draw stuff in 3D, but if we reduce it to 2D, we will definitely be able to draw it. So there's a few strategies that I recommend. A strategy that I recommend is, well, you can just plug in numbers. So like what you can just plug in numbers to figure out which one is higher and which one is lower. So that's how you will decide your balance for dz, dy, or dx. Is you have to have the lower one in the bottom and the higher one on top. So if you plug in numbers, usually the bottom or the top will be something very nice, like z equals 1, or z equals 4, or z equals like 1 minus x, something that you could kind of, it's more tangible, and then you can just plug in a number that you know is in the region, and you'll be able to find out whether or not it's greater than or less than. So then you'll be able to place the numbers in the correct place when you're setting up your integral. Now, with stuff like this, it's a little bit easy to draw, so let's draw it. So for this one, it's a plane, as established from 12.5, or not 12.5, 1.5, equations of lines and planes, or no, not 1.5, like 1.3, I think. This is an equation of a plane. 1, 1, specifically, if I put x equals 0 and y equals 0, it has a z-intercept of 1. If I put x equals y equals 0 and z equals 0, x-intercept of 1, and the y-intercept is also 1. So it actually happens to be this right here. And why do I draw it like a triangle like that? Because you'll soon realize that the volume is in this triangle. I'm going to use green for volume. This triangle and the coordinate planes is where the plane is, or the cube is bounded in. Of course, I can draw the entire like plane, but what's that going to help me without drawing the triangles to indicate when it crosses the xy plane, the yz plane, and the xz plane? There's no point. So I just drew this triangle to indicate the plane and where it passes those 3 coordinate axes. So that's a lot more helpful. Now, if you view this plane, the thing that I suggest, and the thing that many professors suggest is, I'm not a professor, but the thing that many people suggest is, if you can evaluate stuff like z simple, you should evaluate it z simple. So if you look at this thing right here, I can evaluate the z simple. I can start from the bottom and then make slices up top. Make slices go up. Start from the bottom and touch the plane. Touch the plane. Touch the plane. Touch the plane. I can evaluate a z simple. There's a clear function at the bottom where every one of these heights touch, and it touches a clear function on the top. It does not change functions. It's all the same function. All of these heights from z equals 0, which is the xy plane right here, z equals 0. All of the heights from z equals 0 touch the tetrahedron. It does not touch any other function. So therefore, we can set this thing as z simple, dz first, and take the integral. And what's the integral? Well, in order to get a function of z, is dz means that we have to have functions of z, no, not functions of z, I'm sorry, z functions, z equals functions. This is not a z equals functions, but I can make it a z equals functions very easily. I can just do this is z is equal to 1 minus x minus y. So you'll get 0 from 0 to 1 minus x minus y dz. Nothing inside because, or 1 inside, but there really is nothing inside because the integral, just by putting it like this, it means 1. I'm going to do dy next, because once you've established the dz slices, what do you do next? You actually project it. You project the xyz space that you have into the plane. In this case, we already know that z is equal to 0, so z is equal to this. So we plug in z is equal to 0, and what do we have in the xy plane? Let me draw the xy plane. X, y. So if z is equal to 0, then we have x plus y is 1. We have x plus y, oh, okay. When z is equal to 0, x plus y equals 1. Right? So this is the projection that you will get right here. If you look from the top, like if you look from the top, if you look from the sky down onto the earth, this is the shape that you will find. Or well, not like this, more like this. It's a triangle, right? So this is the shape that you will find. I'm actually going to highlight this yellow this time because it's a area, not a volume. So now you can just evaluate it like you've evaluated double integral. And I'm going to do y simple because I'm more used to y equals functions than x equals function. So this is the integral from 0 to 1 minus x. And this is the integral from 0 to 1. Why? Because this is y equals 1 minus x, and the slices go from 0 to 1 minus x. And then when you add all of the x's together, you will just add from 0 to this point right here, which is 1. So that's the volume. dz, dy, dx. Which is what? Which is the integral from 0 to 1 of the integral from 0 to 1 minus x of z from 0 to 1 minus x minus y. I'm not going to waste time. I'm just going to say that that is this. dy dx. You evaluate triple integrals the exact same way you evaluate double integrals. It's not very hard. Okay, now it gets a little bit more tricky because... Oh gosh. Alright. Now it gets a little bit more tricky because this is equal to the integral from 0 to 1 of y minus xy minus y squared over 2 from 0 to 1 minus x. Just a little bit harder to calculate, but this is equal to 0, 1. You can do this with a double integral. In fact, you can actually do this question with a double integral. And that's why this might be a little bit excessive. To do this with triple integral, what you can do is you could just find the volume under the surface, and our region would just be this triangle, which is what we're doing basically right now. Our region would just be this triangle right here, and you can find the volume under the surface 1 minus x minus y, and you'd only have to do a double integral rather than a triple integral, which is what you'll get if you set it up correctly. You'll get this. So that's actually pretty interesting as well. But yeah, you don't have to do this much work to get the triple integral, to get the volume. You can just do the double integral instead. But with the mass thing, you will have to do it. You will have to do it this way. So this is 1 minus x minus x minus x minus x plus x squared. This is x squared minus 2x plus 1. So it's minus x squared over 2 plus x, and then minus 1/2 dx. Yeah, please, if I make a mistake, please correct them for me. I am not very good at arithmetic sometimes. So there you go. And that's equal to the integral from 0 to 1 of, well, 1 minus 2x, 1 minus just 1x, or I'm sorry, 1 minus 1 half is 1 half, minus x plus x is minus x, plus x squared is plus x squared over 2 dx. And this is actually really nice. It comes out to 1 half times x minus 1 squared. You guys can 1 half times x minus 1 the quantity squared. That's actually you guys can confirm that. That's pretty interesting, in my opinion, how it can become that. But you guys can confirm whether or not that's true or not. Okay, so that's equal to 1 half x minus x squared over 2 plus x cubed over 3. No, not x cubed over 3. I'm sorry, x cubed over 6. Alright, so what will this give you? This will give you, or evaluate from 0 to 1. This will give you 1 half minus 1 half plus 1/6. And I can do minus 0 plus 0, but I think you guys get the point. So the volume is 1/6. And if you use traditional ways to calculate the volume, like 1/3 base times height, you will find out that the volume of that is also 1/6. Alright. This is a little bit harder. Actually, this is way harder. Find the mass of the shape bounded by z equals x, z equals 2x, y equals x, and y equals x squared when the mass density function is rho of xyz equals x squared plus y to the third plus z to the fourth. In fact, I'm gonna change that a little bit. I'm gonna change it to y squared because I don't want the 0 thing to happen again. All right. Actually, I don't think the 0 thing will happen. Whatever. I changed it. So it looks like that. So this is the boundary right here. Let's draw it. Let's try to draw it at least. If we can't draw it completely, we'll try at first. Remember that we want to do things in the z simple way as much as possible. So z equals x is what? Well, if that's the x, y, and z, z equals x, if you just like spin the graph a little bit, if you have right here xz plane, this will be z equals x right here, and z equals 2x would just be something like this. So z equals x will be something like this, and z equals 2x will be something like this. Right? If you take this graph and you spin it so that the xz plane is like this and the y is like this, then that's what you're gonna get. Or I'm sorry, the y is like this. So that's the z equals x, z equals 2x, those two lines. And actually, I'm going to draw the entire plane as well. I know I said I wasn't supposed to draw the entire plane, but it looks like two sheets of paper, right? Or like when you flip a book, it looks like two kind of planes. One is clearly lower than the other. But I still want to draw the shape. So what's the shape going to look like? Well, let's draw y equals x. Y equals x looks something like this, right? It's just the y equals x plane. And y equals x squared looks something like this. So this shape looks a little weird. This is the projection. You could see, right? This is the projection right here in the xy plane. And it goes something like this. So let me try to draw it well, at least kind of semi-well, for you guys to see what the shape looks like. Yeah, it looks it's strange. It's a strange shape. All right. So if I draw this line right here, then I'm gonna assume that that's that, and then if I draw a all right, let me actually get rid. So like something like this. Like this. All right, let's just do that. Whatever. And then That's kind of the range of the shape right there. And it looks something like this. Kind of builds down. Um, and then this side... wait. So yeah, so like, it looks something like that. And then something like that. Yeah, quite an obscure shape. No, I need green. This right here looks like the shape. If you can visualize it, that's great. If you can't, it's hard to visualize. Some shapes that you do will be very hard to visualize. It's this shape right here. It's basically the little quadratic slice between two sheets of paper. That's definitely very hard to visualize. So I do not, I'm not gonna blame you for not knowing what this shape is. But I will blame you if you don't know how to set up this integral, because you have to know how to set up the integral. How do you set up the integral? You take the lowest x, or in the region, you take the lowest z, and then the highest z. So lowest z is not z. Lowest z is z equals x. Z equals 2x. And then you have x squared plus y squared plus z to the fourth. And then, yeah, now it's a little bit more simple. Now we can actually visualize it in the xy plane. And it's just y equals x squared. Which one's the lower one? It's the x squared. 2x dy. And then finally, x and x squared intersect at 1 and 0. So 0 to 1 is our range. And there you go. That's a little bit obscure. A little bit of a strange shape. I'm actually pretty proud of the drawing that I drew. But let's evaluate the integral now. So this is equal to the integral from 0 to 1 of x squared x. So we have x squared z plus y squared z plus z to the fifth over 5. Evaluated from x to 2x. dy dx. I need to put dx right here, dy dx. If I put 2x and then minus x, I'll actually just get x cubed. So that's what I'm going to do to make this a little bit quicker. 0 to 1, x squared 2x. X squared times 2x is 2x cubed, minus x squared times x is x cubed, so it's x cubed, plus xy squared. And then plus 2x to the fifth is 32 over 5, x to the fifth. And then minus 1 over 5, x to the fifth. So it's plus 31 over 5, x to the fifth. Dy dx. Now we continue the same thing. This is the integral from 0 to 1 of x cubed y plus x y cubed over 3 plus 31 over 5 x to the fifth y evaluated from x squared to x dx. Now that you're gonna get a lot more creative. You're gonna get a lot more creative of I cannot. This is annoying. This is really annoying. No, I don't want to group all of them. No. Okay, I'm just gonna redraw it. This is ridiculous. Yeah, so plus z to the fourth dz dy dx. So you're gonna, like, I can't actually do mental math on this because I actually have to calculate it out. It's a little bit more complicated than that. So it's x to the fourth plus x to the fourth over 3 plus 31 over 5 x to the 6th minus x to the 5th plus x to the 7th over 3. And then if you put x squared right here, you will get plus x to the 7th over 3, x to the 7th over 3, and then you'll get plus 31 x to 31 over 5 x to the 7 dx. And I would not simplify this, I would just evaluate it as is. So this is equal to x to the 5th over 5 plus x to the 5th over 15. So that's the mass of the shape, and I'm not simplifying that. That's ridiculous. Alright, so conceptual check. Can these integrals exist? I'll give you guys like 10 seconds to think on whether or not why these integrals would be possible or not. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You can pause if you want more time. But this integral is not possible no matter what dv you get. No matter if you have dx dy dz, or dy dz dx, or dz dy dx. Not possible. However, this integral is possible. And this is possible if it's dz dy dx. Exactly. Has to be dz dy dx. Why? Because z is equal to these functions right here. You're taking the lowest z to the highest z. If you had y equal to these functions, you're taking the lowest y to the highest y. But we have a dependence problem because y is expressed in terms of y. So that doesn't make sense. That's why we have to have z functions right here. And when we evaluate all of our z's, we can't have any more z's in the function. Otherwise, what we're going to end up getting is variables at the end of the problem, and that doesn't work. We're supposed to get a number. We're supposed to get a mass or volume, or a charge, like amount or whatever. We're not supposed to get a variable, a function. So y is equal to these two, and then x is equal to these two. For this integral, you can't do that. Why? Because it like even if you have dx, dy, so yeah. So for the first integral, the two choices you have is dx or dz. If you have dx, you have this x equals 3, x equals y, and then you'll have y equals y plus x. You can't do that. That's a dependence problem. If you have z first, z equals y plus x. That sounds promising, right? Well, it does sound it sounds pretty promising, but then you'll have dy at the end, but then you'll still have x variables, right? So if you integrate this, and then let's say you integrated, I don't know, y plus x to 1, and then 0 to 1 of just the area, dy dx. You first integrate this, you'll have 1 minus y minus x dx from 0 to 1. What you'll get? You'll get x minus yx minus x squared over 2. And then you'll plug in all of your 1s, you'll get 1 minus y minus 1/2. You'll end up with a y, and that's a variable. You can't have that. So the rule of thumb is that you can only have as many variables as the dimension allows inputs, which is a little bit weird to say, but this right here, the first two, the double integral, is the domain, the function is has two inputs, so it's a 2 variable thing. R2. And I'm going to use these R2, R1, right? I think you guys already know. This is R3. It just means 3 dimensions, 2 dimensions, 1 dimension. If it's in R3, one of our dimensions is already occupied with z or y or x. Z equals something, y equals something, x equals something. So if we evaluate with more than 3 variables in R3, that's not possible. Because where'd the other dimension come from? It came from nowhere. We're not summing anything. Doesn't really make sense. Similarly, in R2, we can't have more than we can't have more than one variable in the bounds because one of our variables is already the x equals or the y equals or the z equals, right? So if we, yeah, there's two variables. There's really, if you look at it on the surface, 3 to y, 3 to y f5 x dx, you look at it on the surface, you think it's only one variable, but no, there's two variables because dx, right? X equals 3, x equals y. So there's two variables right there. You can have three variables for your first integral in a triple integral, but you can't have four. You can have two variables in your second integral, not in the bounds. You can only have one integral in the bounds, but your second integral can be hidden. It's the dy. You can have two variables, but you can't have three variables. You can have one variable at the end, which is only the z equals, or the y equals, or the x equals a constant. So the end integral has to be a constant. This one, why does this not work? Because there's a dependence relationship. Two, if you do y is equal to y plus x, you will end up with, or no, if you do y is equal to y plus x, the function over here clashes with the dy right here. So you're adding up all of the changes in y in y. Doesn't really make any sense. So this is not possible. Really, like, if you don't understand whatever I was saying the past 5 minutes, just remember the first integral cannot be this integral, cannot be this differential. It's the same not function, the same variable as this, and it can only have two variables in the bounds, not counting x equals. So if it's just written to you as a question, this integral can only have two variables in the bounds, this integral can only have one variable in the bound, and this integral can have zero. The last integral has to be all constants for the integral to exist. Now, I've been doing xy planes, and I've been telling you that z simple is the best way, but sometimes it's not. And this is the time when it's not the best way. So let's find the mass of the shape bounded by y is equal to 1 minus x squared minus z squared. Y is equal to 1 minus x squared minus z squared, and y equals 8, or negative 8. So let's do it. Let's do this. What's y equals 1 minus x squared minus z squared? If you did 1.4 well, if you remember 1.4 well, you will remember that that is a paraboloid, right? A paraboloid right here, like this. It looks something like this. It opens in a negative y direction because of the negative, like 1 minus x squared minus z squared. So it opens in a negative y direction, and it touches the plane y equals 8. Or sorry, not y equals 8, y equals negative 8. So what does that look like? That looks something like this, right? It's actually a circle, perfect circle. I actually drew that circle really well. I'm really proud of that again. I keep surprising myself today. Anyways, so what does this mean? How does this work? If you look at it, is this region x simple? Does this region look x simple? Does this region look z simple? Well, yeah, it does. It looks x simple and it looks z simple. But here comes the problem. The problem is I can solve this for x, y. I'm sorry. I can solve this for x. Y minus 1 is minus x squared minus z squared. 1 minus y is x squared plus z squared. 1 minus y minus x squared is z squared is x squared. Same thing for x. You will get the exact same result for x, just switch x with z. X is equal to plus or minus square root of 1 minus y minus z squared. Yeah, I can do that, but it's going to be a pain to integrate the second integral. The first integral I think is fine, right? This is the mass of the shape x minus y minus z. Looks innocent. It's fine for the first integral. But then the second integral, I'm going to have to, at worst, FOIL out squares, and at best, or at best FOIL out squares, and at worst, integrate with the square root. And I don't want to do that. I don't want that to happen. So they already gave us two nice functions of y in terms of x and z. So that's what we're going to use. We're going to use functions of y in terms of x and z. Specifically, we're going to make it y simple. So what we will end up having a projection into an xz type plane after this. So that means our slices are like this. So where does it move? It moves from where's the lower bound of this? The lower bound is the plane, and the higher bound is this paraboloid. So y, so dy integral x y z, dy integral will be 0 to 1 minus x squared, or no, I'm sorry, minus 8 to 1 minus x squared minus y squared, or 1 minus x squared minus z squared. So let's do this first. What is this? This is equal to, or yeah, I'm not gonna do that first because that's actually quite. No, sure, I'll do that first. We're not in a classroom. It's illegal, but I don't care. So this is equal to xy squared over 2, or I'm gonna put the 1/2 outside. Z evaluated from -8 to 1 minus x squared minus y squared, or 1 minus x squared minus z squared. Which is equal to 1/2 times x times 1 minus x squared minus z squared squared. Yeah, that does not look very fun to integrate. Minus 1/2 times x times 64 times z. Alright. How do we FOIL this? I'm just gonna FOIL real quick. You guys can work on it you guys can work on it if you want to, but I'm not going to waste time. I'm just gonna FOIL it in my head. This is 1 plus x to the 4th plus z to the 4th plus x 2x squared z squared 2x squared z squared plus 2x squared plus 2z squared. And I actually need to fix some of my signs because some of them are wrong. These are all right. X squared z squared should have that sign, but x squared and z squared should be negative. And then it's just 64 at the end. So yeah, minus 64. That's equal to 1/2 times xz plus, or no, I'm gonna distribute. This is equal to, yeah, 1/2 xz plus 1/2 x to the 5th z plus 1/2 x to the z, xz to the 5th plus 1/2, or no, not 1/2, plus x to the 3rd z to the 3rd minus x to the 3rd z minus z to the 3rd x minus 32xz. That's a big number. That's a really, really big number. Alright. So now how do we set it up in the xz direction? And I actually think that we're in trouble. We're in real big trouble. Because the thing that I'm about to do is going to give me kind of PTSD. It's not going to be very fun. So find the mass of the shape. The shape that we have projected onto an xz type plane. An xz type plane, we already have one in our question, and the xz type plane that we have one is parallel to the xz plane is y equals -8. So what we can actually do is put -8 into here to get a 2D projection. -8 is equal to 1 minus x squared minus z squared. So x squared plus z squared is 9. x squared plus z squared is 9 is a circle on this plane right here. So I'm gonna draw a plane. This is not the xz plane. This is the plane y equals -8. X squared plus z squared is 9. So it's this. It looks like this. Oh, that would have been the best circle I've ever drawn, even better than this one. But too bad. You guys are just gonna have to deal with that. So this circle is very nice. It's an XZ plane circle. However, it's not very nice to integrate. And when you see this type of function, you should be screaming polar. Yes, you have to use, or you ought to use polar in this case. So let's use polar. We gotta have like a new type of polar. We have to make our own polar, and the reason is we don't have the xy plane anymore, but z has taken the place of y in this case. So we can say that x is r cosine theta, z is r sine theta. Our Jacobian will not change; it'll still be r d theta, and then what will we end up getting? We will end up getting the double integral of the region R, or the region D, I say, or C, short for circle. So double integral of C of this abomination. I'm not even gonna write it all out. D A, and this is the integral from 0 to 2 pi of the integral from 0 to 3. Oh no, yeah, 0 to 3. Of this r d theta. What is this? This is 1/2 r squared sine theta cosine theta. This will take forever to write out. This will take absolutely forever to write out, and for that reason, I'm not writing all of it out. If you put in all of the x's and the z's, you should end up with not a very pleasant number. You'll definitely not end up with a very pleasant number. In fact, it might be a negative number. But that's for you to find out, because I'm not doing this. This is ridiculous. So that is how you would set up the integral. R squared, 1/2 r squared, cosine theta sine theta. I'll write the entire integral out. 1/2 r to the 6 cosine to the 5th theta sine theta plus 1/2 r to the 6 cosine theta sine to the 5th theta. And that's just 3 terms right there, and it's already this big. Plus 1/2, or no, not 1/2, plus r to the 6 cosine to the 3rd sine to the 3rd. Now you can do some pretty nice things with this, but or no, not x. You can do some pretty nice things with this, but I'm not going to, because this will take at least an hour to integrate, and I don't want to waste you guys' time. Sine to the 3rd minus r to the 4th cosine to the 3rd sine, and then we need to shrink this one once again. This needs to be shrink once again. Right, minus r to the 4th sine to the 3rd cosine minus 32 r squared. Needs to be shrink one more time. Cosine, sine, all of that in parentheses, r dr d theta. There you go. Evaluate that in your free time. If you just put it in Wolfram Alpha or something, I won't even pin your comment. I'll pin your comment if you put it in Wolfram Alpha and evaluate it for me, because I cannot be. It won't appear on the test. I'm too apathetic to evaluate this integral by myself. This is absurd. I don't know why I picked this integral. I have better things to do, and that's gonna be it for today's episode. That I was lucky I made this episode short. But it still ended up taking an hour to record. I'm gonna cut off some bits because my parents interrupted me. But that's gonna be it. I'll see you next time for some more important stuff like cylindrical, spherical coordinates.